Sigma notation. Our goal here is to use sigma notation, summation notation, to calculate the sums and powers of integers. Let me get my notes. How many of you have seen, everything just disappeared. I love OneNote, and I say that with incredible sarcasm. Used to have a really cool program. I'm talking like 5 to 8 years ago that worked really well, and they got rid of it because they want everyone to go to OneNote, and I just hate OneNote. Okay, it crashes on me frequently. I'm making videos, and it crashes. I have to pause or restart OneNote. Okay, so sigma notation is this. It's a Greek letter. This is capital sigma here. And it's what we use for summation. These are adding a bunch of things up. So in this case right here, we have 1 plus 2 plus 3 plus 4 plus 5 and so on. We could write this as, this is the way we set it up with the numbers in different places. In this case, we're adding 1 through 20. So we start at 1, we go up to 20, and we have I. I is the thing being added, and that's what's happening to us. So just that term, it's 1, then 2, and then 3. If we had I squared, it'd be 1 squared plus 2 squared plus 3 squared, and so on. So this is this notation. So this means 1 plus 2 plus 3 plus 4 plus 5 plus ... until we get out to 19 and 20. So that's what this type of notation means. It's a quicker way to write it. You don't have to write as many terms. And then when we do some evaluation, as we get into finding the area under the curve, the exact area under the curve, we will, it's nice to have this notation. We learned some, I wouldn't say tricks, but what summations mean. There's a guy named, who's heard of Gauss before? No one's heard of Gauss? We have to re-import that first one. See, everything, I'm trying to close it out, and it's like everything's disappearing on me. Okay. Start this again. So there's a guy named Gauss, and I've heard this story described different ways. They say when he was in kindergarten, his teacher assigned them a task to add up the numbers from 1 to 100. Have you heard the story? Yeah, a couple of okay. So, and I don't know if it really is kindergarten or if it's like elementary school for Germany, or what the actual grade was. Was he a 5-year-old, or was he like a 10-year-old, or when did this happen? And so we end up using this formula, by the way. So he rationalized that, okay, 1 plus 2 plus 3 plus ... plus 100. You can add that way and just take your time. That's what the teacher wanted. Students do this. I want a break, so have them do that. And then, but he said, what if I list it out this way? Then I listed out this way, 100 plus 99 plus 98 plus 1. Now, if I add all those up, what do I have each time? What's 100 plus 1? 101. What's 99 plus 2? 101. What's 3 plus 98? 101. All the way down to 101. Now, how many 101s are there? Are there 50 of them? Well, you got 1 through 100 terms. So there should be 100, right? I think we might be saying the same thing, so don't think I'm dissing anyone yet. Not that I would diss anyone, but I'm not trying to upset anyone by saying no. So we have 100 of those. However, he recognized we have twice as many now. So divide by 2. And so that would come out to be, I think it's like 50, 51. Is it 5,050? Okay. 100 times 101 divided by 2. And that's the answer. So we can use that formula and just know we're going to be doing some of the stuff later on. If you're adding up 1 through I equals 1 through n for I, that means you have 1 plus 2 plus 3 all the way out to n. The answer turns out to be n times n plus 1 divided by 2. So I'm a little early on showing you that because we're going to get into that later on in this overall section, but I just wanted to share that with you as some of the roots behind it. And it's a pretty famous story. I tend to wonder if it's been embellished a bit, but that's the Gauss story and the sum of the first n terms. Okay, so with that, and you don't have to write this down now, that's coming up, but it's an interesting story. So this is a standard notation to write it where a sub I could be just I, it could be I squared, it could be 2i plus 3, it could be several different things, but that's how we would write it. Or as they show here, that could be S sub I. In this case, they started at I equals 2. That's why it's a 2, 3, 4, all the way out to 7. Just this is a pretty flexible function. Most calculators have a summation tool on them, so you can add up if you have a defined term that is dependent upon which number it is in the order. Okay, so let's do some examples here. Write the sigma notation and evaluate the sum of the terms. 3 to the I for I equals 1, 2, 3, 4, 5. So this is saying, when I read this, this looks like to me that it's saying the sum as I goes from 1 to 5 of 3 to the I power. So what is that saying? That's saying 3 to the 1 plus 3 to the 2 plus 3 to the 3 plus 3 to the 4 plus 3 to the 5. So that a sub I term is 3 to the I. And what would that come out to be? Anyone have a calculator? $363 is correct. Good. Any questions on what that notation means? What went where? We're going to do more of these. So hopefully, if you haven't seen it, understood it yet, it'll become clearer. So this next one is 1. I want to say, given however it thinks it up, you can consider it 1 over 1 plus the 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. Now, if we want to index this, so it goes 1, 2, 3, 4, 5. What do you think that expression is going to be? What's happening to those indices at each iteration, each point? 1 over, okay, good. So we'll call that the sum. I goes from 1 to n of 1 over I squared. And I hear what you're saying, you call it x, and that should be fine too if you index it as x equals 1 to n. So there's nothing magic about this. We tend to index it with I for the term index, and that's what we're calling indexing it as far as those terms, and by like categorizing them, cataloging them, and so on. Okay, questions about that using that notation? Oh wait, my mistake. It goes to 5, not n. So if anyone wants to know, is there something like that for multiplication? There is. It's a capital pi. We're probably not going to use it in this class, but there is something like that. But the summation one works for what we do, because just a preview, we're going to be talking about this area into the curve plus this area into the curve plus this area into the curve, and adding all those areas up. Okay, ready to go on? We have another example to look at. So how would you write this? Now notice where it starts. This is the sum Right, sigma notation, evaluate the sum in terms of 2 to the I for I equals 3, 4, 5, and 6. So how would you express that? Where does I start? I starts at 3. How far does it go? 6. And what is happening to I? So it becomes 2 to the I. So if we write these out, there's only 4 terms, so this wouldn't be too long to write it out. That would be what? Plus 2 to the 6th there. And what would that be? You have a handy dandy calculator. $260, you said? $260. I had something different.
Oh, yeah, I messed up.
I get 120.
Yeah.
Okay. Questions there? Okay, let's go on to some properties of Segway notation. So we're saying A1, A2 through AN, and B1, B2 through BN represent 2 sequences of terms, and C is some constants. The following properties hold for all positive integers n and for m, where m is between 1 and n. And you'll see at the bottom why why they break it up like that. So here we go. We have, if you sum up the constant C, so C is not indexed, it's not something happening to it as far as being squared or cube root or whatever. It's just C plus C plus C plus C, you get n times C. And then you have the sum of I equals 1 through n of C A sub I. You can factor the C out, you can pull it out, and then it's just the sum of whatever's happening with AI. And then if you have the sum of 2 sums of AI plus BI, that's the sum of the AI plus the sum of the BI. And if you have the sum of the difference, again, that's the difference of the sums. And then the last one, you can split it up. So notice it goes from 1 to n, you know, the n is between them, let's say in the earlier conditions. You can go 1 to n of AI plus the sum of n plus 1 to n of AI. That equals the whole thing. So you can break it down if you have to. And I think we may do that at some point. So those are some properties that we can use. I think it's funny that there's a properties of sigma notation that are going to prove properties. Not properties were immutable, but okay. Let's move on. Sums and powers. This is what I was telling you earlier about the Gauss thing. So the sum of I, 1 plus 2 plus 3 plus 4. So I is the index with whatever term we're on. That's going to be 1 plus 2 plus through n. That's n times n plus 1 over 2. And the one that people don't usually know or remember is the I squared. It's a little more complicated. It's n times n plus 1 times 2n plus 1 over 6, right? And then the sum of consecutive integer cubes, so I cubed, is going to be n squared times n plus 1 quantity squared over 4. Okay. Questions there? It's my earlier class today. I'm like, okay, let's wait for people to get on writing. It's not finished. And they're like, yeah, we're done. You're still writing now. No, I'm just doodling. I'm like, okay, so I never know now if people are doodling or still writing notes. Okay, so with that, let's go ahead and go on to another example. So we're going to find the sum of the terms I minus 3 squared for I equals 1, 2 through 200. And then we have the sum of the terms I cubed minus I squared. So we'll look at each of these different separately. For the first one, you have the sum as I goes from 1 to 200 of I minus 3 squared. And it's helpful, and we're going to be doing this when we do actual integration. And let me be clear about this. We're going to learn, remember how we did the long way to do the derivative with all the limits? We're going to do some limit stuff at some point to find area under the curve. It's not the way it goes long term. It's just showing you how it's derived, and then we'll be doing all the shorter, quicker ways to do that. So just want to be clear, and so you're not getting overwhelmed by how this works. So if I expand that, that's I squared minus 6I plus 9. And so I can use that property that lets me split them all up because they're just separated by addition or subtraction. So this becomes the integral. So I goes from 1 to 200 of I squared minus 6 times the sum. I goes from 1 to 200 of I plus the sum as I goes from 1 to 200 of 9.
Where'd you get the 9 and the 6?
I expanded the I minus 3 squared.
Oh,
So that I minus 3 squared is I minus 3 times I minus 3. And that's going to be I squared minus 6I plus 9. Okay, so we have 3 things to work on. The first one's the hardest. So that first one, it's an I squared. The I squared falls to this formula here. So the n that goes up to 200, so it's going to be 200 times 200 plus 1 times 400 plus 1 all over 6. Times 201, let's say 200 plus 1 times 400 plus 1 all over 6 minus 6 times the next one is n times n plus 1, so 200 times 200 plus 1 all over 2. And the last one is just going to be 200 times 9 because it's 9 times 9, 9 plus 9 plus 9 plus 9, 200 times. So it's calculator time. I don't expect this to be done in your heads. You want to have a sum for me for the first part, 200 times 200 plus 1 times 400 plus 1 all over 6.
why did you put all that over 6? The first one?
That's the formula
Okay.
right here. N times n plus 1 times 2n plus 1 all over 6. Because this is an n squared or I squared one. Okay. I came up with, was it 2,686,700. The next one is 200 times 200 plus 1 over 2, so that's 20,100. And then that's what, 1,800? I get, so doing all that math, I get 2,567,900. I was tempted to do that one a different way. I was tempted to go from, do the 1 and the 2 separate, and then do 3 to 200, do that sum. And then I could change the index to go from 0 to, what would it be, 197. I was tempted to do that, didn't do that. This is how they want us to do it. And this is actually a good example of some of the stuff we will end up doing at some point when we take limits, expanding things in there. The second one we were looking at, it's I cubed minus I squared. So we're looking at the sum. I goes from 1 to 200 of I cubed minus I.
1 to 6.
Oh, just a 6, thanks. Come on, don't you want to go to 200 again? So that'd be the sum I goes from 1 to 6 of I cubed minus the sum I goes from 1 to 6 of I squared. So we'll use the formulas again that are just above this. So for the I cubed, that's 6 squared times 6 plus 1 squared all over 6 minus 6 times 6 plus 1 times 12 plus 1.
I thought it was over 4.
It's over 4. My notes are wrong then, over 6. It is over 4. I wrote it right in the second one. Thank you for saying something. So we get 1764 divided by 4 minus 546 divided by 6 equals 350. Any questions there? No? Let's try another one then. Ready? Okay, find the sum of the values 4 plus 3i for I equals 1 through 100. So what should we write? How can we split that out?
2 plus 3 times
Times the sum of
100
I like that. And what is the sum of 4 going from 1 to 100? $400, good. 400 plus 3 times what? So we have this I equals the sum 1 to 100. We just did this one earlier. Summing 1 to 100. What do we do?
100 times 100 plus 100.
Okay, good. So I think it's 54 or 50. No, I forgot the times 3. 3 times 50, 50. So that comes out to be 15,550. Okay, should we go on to another one? Find the sum of the values f of x equals x cubed over the integers 1 through 10. I feel like we did harder stuff earlier. So this would be the sum. I goes from 1 to 10. These lights are so frustrating to me. And we call it I cubed. Excuse me. So what's the formula for that? What's the formula for a sum of a cube?
1 squared times n plus 1.
I squared times I plus 1 squared divided by 4. I guess I should just say 10. Did you say 10 or n?
I said n.
10 plus 1 squared over 4. So that's 100 plus times 101, 121 divided by 4, and we get 3025. We got 2 more I want to do in this section. We have another sum. This time they indexed it with a k instead of an I. So k equals 1 to 20 of 2k plus 1. So how would you break that up?
Two times the
Sum.
over
K. Go ahead.
20.
You're right. It's just 20. We need to make it harder. So it's 2 times, and that was 20 times 20 plus 1 is 21 divided by 2 plus 20. It's really those twos could divide out. And I ended up with 440, good. Last one from this section, I think. We're gonna write the sum. This one just writing the sum. So what would go on top and what would go in place of the B? And it goes from 1 to what? 84, and what goes inside this, the summation? I would say I, except they start with an N, so thank you for, not you, but thank you to them for not being consistent. So I'm gonna say N, yes, thank you. So the B is the N, the A is the 84, and that's it for that section. So yay.